so awesome to be here at Serverless Days, Event-Driven Architectures Day, EDA Day. I've already got my events mixed up, and it's only like first sentence I've been talking about. So yeah, EDA Day, hopefully everybody's all right after lunch. Eric talked about the carb coma. I won't point you out if you're going to be snoring, but yeah, if it's going to be really loud, just nudge the person next to you, and then we can wake everybody up. So today I'm going to be talking about serverless compute. And we've been talking a lot about event-driven architectures today, and I'm going to try and bring some of the sort of aspect of the compute part of it, because obviously we've got code that's going to run, we've got something that needs to run to be able to do your business logic. And as Eric says, I'm a developer advocate, so I work within the serverless product team. Sort of two parts of the role. One is cool, is talking at places like this and meeting developers and seeing how they develop applications, and then also working very closely with the service teams internally to make sure that we're building the right applications and right abstractions that you're going to need. So I'm going to do a bit of a sort of quick sort of overview of what is serverless and what is sort of event-driven architectures and how some of the AWS bits and pieces fit together. So serverless, obviously, we know if we're here and if we understand, it's all about giving your development team time focus. Focus away from all the infrastructure, focus away from all the undifferentiated, heavily lifting, all the cruft that you need to build, and being able to focus on your business and to be able to focus on what your applications actually need. And if you heard Dave Anderson's talk earlier, he's written a whole book about that kind of focus, how you can get your organizations to think about taking advantage of the cloud, being able to do as little as possible to get the most bang for your buck. And the serverless approach really helps with that. And at AWS, we've got a whole bunch of serverless services. People think of Lambda as sort of the start of serverless, but actually, we've been building, in a way, serverless services since the very beginning. If you think of things like S3 and SQS, foundational services at AWS, serverless from the very beginning. And yeah, you can see here, a whole bunch of compute things. I'm going to be talking about some of those. But obviously, we've got storage, and we've got different integration services, and database and analytics. And the whole idea is that you can just consume these services, pay when you're not using them, get good value from them, be able to scale up as big as your business goes, and be able to let your developers iterate and have the agility to build new applications as fast as possible. And of course, this all happens at sort of ridiculous scale. And I just picked three of the stats that we've got internally. And Lambda processes tens of trillions of requests every single month. It's absolutely huge. This is all over the world. And EventBridge, we've had a lot of talk about EventBridge today, and that's 2 trillion events per month going through as well. And I'm going to be talking about serverless compute, and part of that is actually the container story. And so ECS, Elastic Container Service, also multiple billions of tasks that are going to be launched every single week. So these are big services that run all over the world and hopefully can support any of your applications. And the sort of value proposition I speak to people about serverless is, why go serverless? We've got technology and we've got compute databases, analytics, and sort of don't forget about all of that, but put that to the side for the moment. The whole idea is to be able to do things quicker. You've got an idea in your business, you want to try something out, you want to experiment, you want to do kind of things, and a serverless approach means, because there's so much less stuff you need to do, you can take this idea, which I often say, from prototype to production really quickly, and sort of have this flywheel that can speed up your organization. So today, Event-Driven Architectures Day, it's all about communicating via events. And so, we've got producers and consumers, and a lot of the talks have been talking all about that. And sort of an event broker in the middle that is going to be the kind of traffic cop that is going to say the events are going to come in, off you go over there, and do various kind of things. And, Amazon EventBridge is our sort of key event router, our key event bus. And of course, it's, really serverless. And it's got these sort of three input things which are super useful. And one is AWS services. So behind the scenes, all AWS services, when they're doing a whole bunch of things, is just going to put a message on that event bus. And we're going to see in a demo later how that is just really easy to set up. And this gives amazing capabilities and powers that anything that happens in AWS, you're going to be able to react to that. You can build applications. Obviously, you can build your own applications, you can generate your own events. Lots of talks all about the order management service and the fulfillment service today, and in many other talks. This is the same kind of thing. You can generate and consume events on your own applications. And also the cool thing is SaaS providers. So a number of SaaS providers, which we have from Zendesk to PagerDuty. I've even forgotten the number. I think there are 30, 40, 50 different SaaS providers. And they just, when an event happens on their side, an event just appears in your event bus, and you can build an application based on that. No webhooks, no APIs you need to run. It's just really easy to be able to consume with that. And the other part of the story we've been hearing a bit about today as well is step functions. And step functions is a slightly different part of it. And this is all about workflows. It's all about orchestration. And that means things that are more tightly controlled. So if you've got a transaction, think of maybe an airline booking. If you book a ticket and then somebody decides to cancel the flight, well, you need to release a seat, and you also then need to release the loyalty points that were accrued for that. There's a whole step-by-step process that is very tightly bound together that needs to do things in a particular order. And step functions is a great workflow orchestration to be able to do that. Other people are using Apache Airflow. That's more of a Python-based thing. But step functions is the really sort of serverless approach to do it within AWS. And in step functions, there's sort of 3 different ways that it can run. And the request response is, think of this as an API. So what step functions is going to do is it's going to call out to something, maybe behind an API or one of these services over here, and it's going to wait for the actual response to come back. So this is when you need to use the response further on in your workflow. Then you've got this, which I always think is slightly strangely named, because it's called run a job, but it's called synchronous. And people get sort of mixed up. They think synchronous should be that request response. But what actually happens with this is step functions is going to pause. So it's going to do something asynchronously, an ECS task. What examples have we got? Athena, we've got SageMaker, all kind of things. It's going to get that task to run and just wait until it finishes and then carry on running. It's not actually waiting for the result of the task that it's getting back into its workflow. It's just waiting for that external task to finish before it carries on. And then a really cool thing with step functions is the sort of wait for callback, and that's sort of commonly called as human in the loop. So if you have some kind of workflow and you need a business process person to sign something on, or a pallet needs to go onto a truck, or a medical diagnosis needs to happen, all kind of things, you can inject these into your step functions workflows, and they can last for up to a year. So with these workflows, you can wait for a huge amount of time, and basically it's just a little bit of text that you pass back to step functions to say, I've done my little piece, off you go and carry on. But this makes it super useful to be able to link these different things together. And of course, orchestration and choreography work really well together. So on the orchestration side, we're often talking about these tightly coupled applications, and often that's sort of generally within a microservice. So if you've got as I was talking about the airline example, often you would have that kind of thing within a microservice that needs to do a few kind of things. Of course, it's then going to maybe talk to other kind of microservices, but that sort of bounded context, if you like, is within a single context, or maybe within one or a few different services. And then Event Bridge sort of expands that out. And this is really about communicating between different services. Now, of course, some of those services can be within a single microservice. We're not going to limit that. But Event Bridge is all about communicating with AWS, with other parts of your applications, with your SaaS partners, between different parts of your organization. And the cool thing is these work really well together. But today we're talking about serverless compute. So what are our sort of options in AWS to be able to talk about how we can actually process your custom code? Because whether you're running step functions or you are running Event Bridge, ultimately you want to react to that business logic. You've got something coming from a SaaS partner, or you need to release a loyalty point, you've got a database to write to, read from, do some kind of thing, you need to do some analytics. There's often some compute that's going to be involved. And in AWS, we've sort of got the serverless landscape we like to talk about, where on the y-axis, we've got sort of what you manage, going from very little to much more, and you've also got this opinionated, going from less opinionated to more opinionated. So Amazon EC2, renting VMs in the cloud, super scalable, lots of different options, lots of different t-shirt sizes that you can do, but there's obviously more that you're going to manage. You're going to manage the networking, you're going to manage the operating system, the patching, you've got armies, you've got all these kind of things that you need to look after. And then, obviously, it's less opinionated because you can run anything on it. And as you sort of go up this sort of evolution landscape, you've then got ECS on Fargate. So ECS is the container service. We're going to talk about that. And Fargate is the container serverless compute service. And in a way, well, it's obviously less to manage than EC2. You're not thinking of instance sizes and all those t-shirt sizes. And it's a little bit more opinionated because you can't run every single workload as you would on EC2. And then Lambda at the sort of top right, well, this is way more opinionated. You've only got a certain number of languages that are managed runtimes. You can run your own language as well. And then obviously there's an event object, and Lambda sort of works in a slightly different way. And it's just a bit more opinionated that you can do. But the cool thing is you've got way less to manage. There's nothing to patch. There's nothing to look after. You don't need to think as much about scaling. You don't need to think about as much as integrations. And you've sort of got this kind of evolution. And that's part of what your business is thinking as well, is do we need more of that control? Do we need to do things more on EC2 because we're keen for the bare metal? We've got, maybe that's for good reasons. Maybe you've got ridiculously high throughput applications and you need the power of EC2, or you're doing various machine models on GPUs and you need various combinations of memory and hardware and that kind of thing. Or do you just want to, I want to worry about my business logic. I want to worry about my code. Please, AWS, just handle that all for me. I know it's going to scale. It's going to be really cool. And you go along Lambda. And then there's part in the middle where you can use containers with ECS and Fargate. And so the first service I am going to talk about is Lambda. And when you talk about containers versus serverless, well, Lambda is about serverless functions. And just hands up in the room, has anybody used Lambda? Cool, most of the room. That's good. Otherwise, we'd be starting from scratch. So Daniel in the front over here says no, and he's like, I think you're a hero, aren't you, Daniel? You've got to worry about that. And so Lambda works in this simplistic but cool, simplistic way that you've got an event source which is going to kickstart a Lambda function. And this event source can be a whole bunch of kind of things. It can be hitting an HTTP endpoint, so something behind an API. It can be changing, it can be reacting to a database notification. So DynamoDB, for example, a record updates and changes, Lambda function starts immediately. It can be uploading something to S3. You upload a file to S3, and a Lambda function runs. And there are so many integrations, I can't even remember how many there are, which will automatically kick off a Lambda function. Very little configuration code you need to do that. It's just going to do that. Your Lambda function is going to then run, and it's going to be run in any of these managed runtimes, even from Ruby, Node, Python, Java, all the popular ones. And also you've got you bring your own, which is a sort of operating system runtime we have called a custom runtime. And so you can literally run any code. I mean, COBOL, Erlang, the whole thing, PHP, PowerShell, anything, any language you can run on Lambda. And then obviously your code is going to do its business logic, and then what's it going to do? It's maybe going to write something to an API, it's going to do something in a database, maybe it's some machine learning inference it's going to do, any kind of thing that your normal code would do, that's going to run in your Lambda function, and it's going to then maybe talk to another service. And there are three ways that Lambda you can invoke a Lambda function. One is synchronous. So think of this as behind an API. You do a request response. So do something behind an API. Lambda function runs. Maybe it's going to grab something from a database. Maybe it's going to pull something from an API, connect some things together, and return you the response. The second one is asynchronous. So this is obviously very popular in the event-driven architecture space, where maybe something like EventBridge is going to put a message on the event bus, and that's going to trigger off a Lambda function, and off you go, the Lambda function is going to do something. The difference between that is that the thing that is initiating the Lambda function request doesn't expect an immediate reply. It's sort of set it and forget it. I've got an EventBridge notification. I'm going to send it to my Lambda function, send it to the Lambda service, and Lambda's going to, I've received your request, trust me, I'm going to handle this, and then it's going to carry on asynchronously and do the process. The benefit is your, whatever the caller service is going to just be able to carry on regardless. It doesn't have to wait for that asynchronous process to finish. And then there's another family of Lambda that works, where Lambda runs some polars on your behalf. So if you're using Kafka, or if you're using SQS, or MSK, or DynamoDB Streams, or Kinesis, all these kind of things, Lambda runs a polar. It's going to pull the records, pull the messages from the queue. You're going to be able to iterate over it within your Lambda function, maybe write the data to a database, or do some analytics or some queries, and then you're going to, and that polar is just managed for you. The scaling and everything manages for you really easily. And so actually what I'm going to do is I'm just going to show you a bit of Lambda scaling, and I'm just going to kick something off, and then I'm going to come back. So basically I want to show how Lambda scales, and I've got a command here that I'm going to run, and it's called hey, and it's going to run 10,000 sustained requests every single second for 5 minutes to this particular API. So it's just an API gateway endpoint connected to a Lambda function. So I'm going to get that to run, and then I'm going to talk about Lambda scaling, and we can actually see that going in action. So one of the reasons people are really keen about using Lambda, other than all the managed runtimes and not the patching that you need to do and all the stuff that gets looked after, is all about Lambda scaling. And this is really cool because Lambda just scales from the get-go. You don't need to pre-set up anything, and off it's going to go. And Lambda's going to initially is able to scale up to 1,000 concurrent requests every 10 seconds. So when I was talking about that event trigger to a Lambda function when it's going to do something, that is one request. So a Lambda function runs for a single request every single time. So without you having to do anything, a single Lambda function can just run 1,000 of those at the same time. You don't even need to do anything. And then every single 10 seconds, you're allowed to add another 1,000 to that. So you can imagine how this can build up really quickly. And this is a new scaling mechanism. I'll show you what it was before just to compare. And of course, this is super useful if you've got varying traffic patterns. If you don't know how much traffic you're going to have, you can't pre-plan, you can't predict. this is really great because you just let Lambda figure it out. That's not going to be a problem. And the cool thing is Lambda is going to manage this automatically without having to do the complexity. You don't have to manage the scaling. You don't have to add stuff. You don't have to remove stuff as it goes along. And so just before reInvent last year, which is in November, there was our scaling worked in a slightly different way. And there was a sort of concept of burst where you had a sort of initial burst of concurrency, burst of scalability, and then this sort of stepping stone that would allow you to add more concurrency per minute. And this was cool. I mean, super high, still super high throughput, but of course we thought this is AWS. This is Lambda, we can do a little bit more. So if you look at this example, if you wanted to have, say, 10,000 sustained requests that were happening all the time, it would literally take 12 minutes to get up to that. I mean, not the end of the world. This is obviously starting completely from scratch. If you were running a production application that was always getting 10,000 requests, well, that first 12 minutes happened 7 hours ago, and your Lambda function is going to be able to have way more requests, and it's just going to scale automatically from that point. So this is literally from a standing start, as if you're doing sort of the 100 meters. Everything is stopped. It would take you 12 minutes to get to 10,000 sustained requests. So now we can improve that. So why don't we do it, instead of having that sort of slower staggered approach, we'll just have 10,000 every single 10 seconds. So this means today, you actually are able to get 10,000 sustained requests in 90 seconds. And this is literally one of the fastest ways you can get a whole bunch of compute capacity in the cloud. Now, also remember that the previous scaling quotas were all to do with all Lambda functions within an account, within a region. Now this is per function. So if you have 100 functions, if you've got 1,000 functions within your accounts within a region, this is the same scaling behavior. So Lambda can dramatically scale on an individual function basis. Yeah, super powerful. So let me just go back to the demo and see how this has actually been working. So this has been running. I've probably been jabbering on for more than a minute and a half, and we will see my Lambda concurrency, of course, is doing absolutely nothing. Let's just refresh that. Oh, there we go. So we can see here, let me take a look at the lines, and we can see that the concurrent executions is blue, and the number of throttles is going to be orange. So we can see here that hey command was going to immediately go to Lambda via API gateway and say, I want to do 10,000 requests. And you can see, initially there was a bit of a throttle. I was like, hang on. I can only do 1,000 every 10 seconds. Just hold your horses. I'll get you in a minute and a half. And you can see how the scaling sort of graph went up. And we could see, what's this, 1250, and it started at 1230. Yeah. So about 90 seconds, we're now able to have 10,000 sustained requests. And you can see this was the throttle. Originally, it had to throttle, and that throttle drastically goes down. So in a minute and a half, I had I've got a massive sale at 9 o'clock in the morning. I've got a hit TV show that's happening. I've got a book that's being released, selling concert tickets and whatever. Totally unexpected. Didn't think about that. And within 90 seconds, I can handle 10,000 sustained requests without having to even do or think about anything. And there are even other ways you can use Lambda where you can actually pre-provision. It's called provision concurrency, where you can say, I know at 9 o'clock I'm going to have a 10,000 requests, so set that up 90 minutes before 9 o'clock, and I'll be able to scale that up really quickly. So that's just a quick way to show how quickly Lambda can scale. We've also improved Lambda scaling for some of the event source mappings. So this I was talking about earlier, if you're getting messages from Kafka or SQS or DynamoDB streams, and this has also been improved. So I wasn't going to just show another demo because I think the graph just explains it. This is a SQS queue, and I think there are 200,000 or something, 200,000 messages within this queue. And you can see Lambda's going to see the 200,000 messages in the queue, and eventually it's going to go, okay, there's still more messages in the queue. I'm going to add more Lambda functions, and this blue line is going to show that scaling up until it eventually processes the whole queue. And of course, we decided surely we can improve that. And so we came out with some SQS scaling, which is far more aggressive in being able to tackle that queue. And you can see how sort of far more vertical that blue line is. It's going to see the 2 million messages in the, 200,000 messages in the SQS queue, and far more aggressively be able to scale up Lambda functions in parallel to be able to handle that. And here you can see, actually, I think it's 1,250 Lambda functions that ran for this particular SQS queue, and that's the maximum that can come up. And this is even more powerful because even though I mentioned earlier about a single invoke for a single Lambda function, when you're using these polling architectures, you can also batch things together. And you can have up to 10,000 items in a batch. So you can imagine the amount of scaling you can have for Lambda if you had 1,250 invokes and 10,000 items in that batch. That is a huge amount of computing power you can get. And some of the controls where you can set things, because one of the cool things about Lambda is this crazy scale, but one of the bad things about Lambda is, oh my word, I've got a database, I've got an API at the other end of it. That's just going to completely kill my third-party SaaS integration. It's just going to completely make my database fall over. And so there's some settings you can do to control this concurrency. So on the event source mapping, for example, you can tell SQS that, you know what, I've got a downstream service that can only handle 50 concurrent requests, max that out at 50. It doesn't matter how many messages arrive in SQS, I'll protect the downstream resource. And then also on the Lambda function side, which is not quite as applicable for the event source mappings, but maybe you've got an API gateway or you've got an asynchronous thing, you can also set a reserved concurrency on the Lambda function. It does two things, protects that Lambda function concurrency to say, regardless of anything that happens anywhere, nothing is shared, I can always ensure that that Lambda function has, for example, 50, and can never go beyond 50, and always has 50 available for it. So just some configuration things that you can have a bit more control. We also improved Kafka scaling, so obviously Kafka is all about high-scale event-driven architectures and processing, and we've also look at that vertical scale. Very annoyingly, the colors inverted on this one, so the orange is the Lambda concurrency, and you can see how that shoots up really quickly. So let's start sort of switching over and talking a bit about ECS on Fargate. And we've talked about all the Lambda function side, and that's on the sort of serverless functions. Let's talk a bit about serverless containers. So Amazon ECS is a serverless container orchestrator. So what does that mean? A few words in the sentence. Well, it is serverless because the Amazon ECS by itself, and I'm conscious that I'm standing in front of the slides, I sort of realized, sorry about that. The concept of the serverless side is that actually ECS itself is entirely serverless. There are no cluster versions to manage, nothing to think about. There's no data store that you need to manage or maintain. There's nothing on ECS you need to worry about for some infrastructure to ensure that that's going to scale. And the cool thing is it's actually entirely free to use. So it's a managed service where it orchestrates containers. We're going to get into that. And if you're using EC2 or Fargate, we're going to get more into that. It's just a service that you can use. And it's an orchestrator because it doesn't run containers itself. It sort of places containers where they're going to run and handles the starting and the stopping of them. And it works with these different compute types. And the main two compute types is it can use EC2. So that's obviously not very serverless at all. But ECS as a serverless container orchestrator can work with EC2, but can also work with Fargate. And AWS Fargate is the serverless compute option. We're going to get more into that. So Fargate is this compute engine for containers. So instead of being the orchestrator, this is the engine for containers. Again, managed by AWS, no armies that you need to manage, nothing that you need to provision or any instances, and it just scales as you need it via AWS. And so Fargate is this sort of kind of weird service. Lots of people say, I'm using Fargate, but you actually don't interact with it. Fargate isn't a service that you find into the console. You don't really see Fargate, you don't interact with Fargate at all. It's just ECS as the control plane allows you to run your containers in Fargate without you having to think about capacity and where those containers are going to run. And so, yeah, you don't have to integrate it with it directly because we're going to do that on your behalf. And so hopefully you can sort of do the mental picture of ECS is this control plane and Fargate is the data plane. So the control plane, if you're unaware, is where things are going to be controlled, where things are going to start, when things are going to stop, when things are going to be configured, permission constructs, and a whole bunch of those things are going to sit at the control plane level. And the data plane is where the data is going to move. That's the sort of where your container is actually going to run, and it's going to take inputs, and it's going to do outputs, and all those kind of things. So that's how you can sort of think of how ECS and Fargate work together. So on ECS. So ECS, also like a lot of other serverless services, is deeply integrated with other AWS services. And so on the sort of left-hand side, you've got some of the build kind of things. So you've got a container registry. This is Amazon's equivalent of Docker Hub. And we've got different code services and CloudFormation that you can obviously use to define your applications. And then on the run side, containers is slightly different from the Lambda perspective. Lambda, you have that one event that comes in and your Lambda function does something. Well, containers do a lot more. And containers often run a port that can be run. It's a sort of more port and socket model, which means there's obviously a lot more networking involved. And that, the power of the different kind of networking is what you can use with these serverless services. And ECS has sort of some cool unintegrations, like the secrets manager. So it can just populate an environment variable with a secret parameter that you can use for an API key or to do whatever you're going to do. And then, of course, in the container world, lots of third-party tooling, lots of open-source tooling. So, Fluent, Prometheus, and Grafana on this slide, as long as the AWS option of CloudWatch, just to be able to do your monitoring, just to be able to do your observability. So, lots of integrations that ECS is able to handle. let's just look at some of the sort of core constructs of how ECS is put together. So an ECS task is one or more containers. So this is the sort of building block of things you're going to have. You build a Docker file. It's a standard Docker file. It's a container, and you're going to store that in an Elastic Container Registry, and you're going to be able to just define what your application is going to do. And that container task is going to specify your Docker file and also compute. So how much CPU, how much memory, network and configuration, security, and all the other configuration about an individual task. And then those tasks may run in isolation, but they also may run as services. And this is cool because you have identical tasks. Think of it if you are running a load balance website. You may have 10 containers that need to spin up to handle a front end for your website. Well, you're going to run a service that is going to do that. And the service is going to be clever, because if a container is going to die, what does it need to do? It needs to spawn up another container, and it's just going to manage those individual tasks, but at a sort of bigger service level. And then also the last little bit is then a cluster, and this is sort of a grouping of services and tasks. So you can think of your cluster as sort of part of your application construct, and this is then uses underneath the capacity providers in a region, and that is then using EC2 or Fargate, and so you are using the server full compute part of it, or using the serverless part of it with Fargate, and both of them actually have spot options, so it's going to be able to save you money. You're going to be able to, when there's available capacity, you're going to be able to get cheap compute at a quick price, with the caveat that AWS is going to say, no, in 2 minutes I need to take that back, please, somebody else needs it, and you're going to obviously be able to have to handle that within your containers to take advantage of that pricing. Something died. So, as we were talking about tasks and services, what is sort of the kind of difference? And the tasks is on-demand workloads. So this uses the task scheduler, and you can think of this as a one-off job. So you need to run a batch job, or you need to do something, very much in the event-driven architectures world, asynchronously. You're just going to run a single task. But obviously, for long-running applications or things that need a bit of orchestration to be able to make sure they're up and running, those are going to be the services. And those are the long-running apps. And that then uses the ECS Service Scheduler. And it's got this health management component built in. And that's going to do the scale-up. It's going to be able to look at different metrics. It's going to be able to, you can use custom metrics, or you can use CloudWatch, or anything to be able to say, when I get to this, add more containers. When it drops below this, remove any other containers. So it's just a nice way to be able to manage those all together. And you can do AZ-aware deployments. So that means you can spread your website across multiple availability zones, so you're not caught out if something happens. And you can group containers together, and this is more the concept of, often containers don't work in isolation, but you maybe have got a sidecar container, or you've got another container with an observability tool. This is just a way that you can bring those all together. So a task definition, this is just in JSON. An example here, it's got 128 meg of memory. It's it's exposing port 80 using TCP. It's got Nginx running. That's just a name. Network config, the memory, the CPU configuration, and it's going to use Fargate under the hood. So this is just a task definition, and that you can specify. So the task definition is set in ECS, and then obviously under the hood we've got Fargate. And so Fargate is going to be this compute engine that is just going to run your container tasks. And basically Fargate behind the scenes is going to dynamically provision an instance. And so this is going to be equivalent to an EC2 instance. It is entirely isolated to your container, entirely isolated to this task, so it's not sharing any infrastructure with any other accounts or services, or let alone anything else. So, really secure altogether. And you basically configure a virtual CPU and a RAM, and that's then sort of the shared pool between all of the containers in the task if you had those sidecar patterns. So in terms of patching, well, who looks after what? Who looks after what? So AWS is going to manage the underlying hosts and the infrastructure. So I mentioned that there may be some EC2 involved. You don't know. You don't care. AWS is going to manage. It's going to have a whole sort of pool of resources across all of our regions that we're going to manage to make sure they're available. So when you do want to run a task, there is some compute available for you to run. And then, of course, slightly differently from Lambda, you now take on the patching of all the code. So if you are running Nginx, if you are running Node.js or Python, or literally any language in that container, everything within that container is up to you to do some patching. So we look after the infrastructure, the hosts and the servers, and all that networking and storage to look after that. But anything inside your application container, that's up to you. In terms of load balancing and ingress, with the ECS and Fargate kind of model, this is sort of, as you go, you manage this because you want the flexibility. So obviously, client code, you're going to be looking after that as well. And then the load balancing and ingress, you're going to use a network load balancer, or some other kind of service to be able to get your application to be able to talk to your containers. Could be behind API Gateway, which is going to be serverless as well. But whatever it is, you're going to be able to manage that. There isn't this concept of an event just magically arrives in your containers. You have to manage your ingress with you. And of course, AWS manages the instances, but you're going to route then that traffic to your application code. And something within your application code is then going to need to receive that request and do something with it. So in that container example, something like Nginx is going to be able to receive that via a port and socket model and do something with it. In terms of the scaling, well, AWS is going to handle the actual scaling of the infrastructure. So as I mentioned before, hopefully we're not going to run out of EC2 instances in some in regions, but AWS is just going to manage that and make sure that we've got that containers on demand are always available for you. But obviously, you then manage and you decide how many containers you're going to do, and you can set up your scaling for those containers. And there are a huge amount of different ways you can do this. You can use AWS autoscaling. You can use CloudWatch logs and CloudWatch metrics to be able to feed those autoscaling decisions. There are a whole bunch of third-party tools. You can use open source tools. But basically, you talk to ECS and you say, when this happens, add some more containers. When this happens, remove containers. And you manage that scaling yourself. Contrast that to Lambda before, where I didn't do anything, and it just scaled up to those 10,000 sustained requests in a certain period of time. If I was doing the equivalent of Fargate, I would need to have a rule, say CloudWatch, for example. As it went up, it would say, add another task, and then remove it when it was finished. So let's have a look at some of the event-driven architecture patterns that you can actually do with serverless containers. So we were talking about the difference between tasks and services. Here is an example. You can see this is very much an event-driven application. An event trigger happens, and it is going to create an ephemeral ECS task, which is going to process a single event. Sounds a bit like Lambda, doesn't it? Interestingly. So in this example, we've got Amazon S3. You upload something to Amazon S3. It's going to do a notification to EventBridge. And EventBridge is then going to be able to kick off a Fargate task. And maybe your code is then going to write something into another bucket. And you can see here, in order to do the event-driven architecture stuff, you do need EventBridge or step functions to actually invoke the task. There's no built-in sort of task organizer thing like you would in Lambda, which is just going to automatically kick off that function. And this is going to be then for less frequent events. You're not running a service where you need to manage a whole bunch of different containers that work in tandem. And so they're going to be less frequent events. You can have a lot of them, so I don't necessarily think they're less frequent. They can be at sort of high scale, and also longer duration. One of the big things, I'm not sure if I mentioned, Lambda can only run for up to 15 minutes. So anything that you need longer than 15 minutes, you've got two choices. You either break it down into smaller tasks that fit within the 15 minutes, or you consider something like ECS and Fargate, where you can run long-running tasks that can basically run forever. So on the services kind of side, you can see this is an example over here. So I have an SQS queue. Maybe it's going to be a super high-scale SQS queue, and I have a whole bunch of tasks that are polling for messages from that SQS queue. So I'm not using a managed integration. The reason I'm going to be using Fargate is maybe each message is going to take longer than 15 minutes to process, or I just have ridiculously high frequency, and that's not going to be best suited for Lambda. So ECS is then going to manage those deployments. So in this example, I'm going to look at the SQS queue. I am going to then monitor the queue depth, for example. If the queue depth is not going to be reducing, I'm going to add more containers to drain that queue. If the queue depth does drop down, I can then reduce the number of tasks. So just a way that you can manage an effective service. Now, one of the cool things with the whole ECS world is actually the CDK. So that's a cloud development kit where you can define your infrastructure in your favorite programming languages. And there are these CDK level 3 constructs, which are actually very well defined for ECS. So you can see here, I have an ECS pattern. I appreciate the text is a little small. It's not sort of that important to see it. But this is defining my infrastructure. So, it's a gig of RAM. It's, CPU configuration telling me the containers, what container I'm going to do, and some environment variables that's going to be set. And then using the CDK code, I can just set this approximate number of messages visible. So this is how much is still in the queue, and there's a direct integration with SQS to be able to poll that, and then decide what you're going to do. So what I'm going to do for this example is, well, actually, if I have I've got a wait, for example, awaiting, I can choose to use Fargate Spot or normal Fargate, and this is just a way I can define in infrastructure as code how I'm going to, what my container is going to do, what its scaling mechanism is, and how I'm going to distribute that compute load. So another use case, for example, could be something like code scanning. So code commit is, a service is going to automatically generate an event to EventBridge. That's going to be really easy to set up. And that EventBridge, again, is going to kick off a Fargate task. And that Fargate task is going to do scanning. Now, this example would probably be longer than 15 minutes. Maybe it's some deep vulnerability scanning, or it's a huge code base or this kind of thing. But the point here is the native integration with AWS code commit, generates an event bridge alert, Fargate is going to kick off and do something. In this case, it's going to then send a notification to SNS to say, yep, my code scanning is complete. So it's about building these event-driven pipelines where we're very comfortable with doing it with Lambda and understanding AWS Fargate as another compute option to expand your possibilities. So I'm going to demo a sort of slightly different one of this shortly with file processing, where you load something into an S3 object, automatically kick on event bridge rule, and this is then going to go to step functions. And step functions is actually going to make a choice. It's going to say, should I use Lambda for this compute, or should I use Fargate for this compute? And ultimately, it's going to put the message in the bucket. Now, in another bucket. Now, in this example on the screen here, what it's actually going to do is say, is this a video? If it's a video, I'm going to use Fargate, and if it's an image, I'm going to use Lambda. Because why? A video is going to be far longer. It's going to take probably longer than 15 minutes, and I'm going to be able to use Fargate for that. And maybe it's not just a time perspective, but Fargate can have a lot more computing power, so maybe you're going to be able to need that. So why don't let's do this and make it happen in action. So I have, that was a previous demo. So currently, in fact, I'm going to go to my code first, and we can have a little look. So currently, it's on the screen. So I've actually set this up in infrastructure as code. I have a CloudFormation template, which is just setting up a bunch of things. And I just want to show you how some of the event-driven stuff is actually quite easy to set up. So for example, I'm going to define an S3 bucket, which I called source bucket, and I'm just going to say here, create an event bridge rule to notify me when things appear in the bucket. That's 3 lines of CloudFormation. I don't have to specify anything else. This is just automatically going to say, for this particular bucket, anything changes in that bucket, let event bridge know. That is pretty cool. I've then got a step function state machine in here. I've got some Lambda functions. I've got some ECS tasks, never mind all that. But the cool thing over here is I can kick off step functions to say, I'm setting up an event bridge rule from S3. Whenever an object is created from the source buckets, I want to then kick off this state machine, step function. That's the second part in the chain. That's very easy to read. You're not creating any polling logic. You're not doing anything. That's a sort of direct integration to be able to connect S3 to Fargate, for example. There are some examples. I've got a Docker file over here for my ECS task. And basically, I've got a step functions workflow that is basically going to check the image size, and it's going to tell me, in fact, this one is a video. So this is going to say, if the video is bigger than a certain size, use ECS to run the task, or I'm going to use Lambda to run the task, and then it's going to finish. And when it's finished, event-driven architectures, either pathway it's going to go down, put something on event bridge to finish. So looking at the step function state machine, I'm going to show what that looks like a bit nicer than the code. But basically, it's just a choice state over here. And this is going to do a choosing and saying the object that arrives from S3, if the size is greater than that, run ECS. Otherwise, by default, run Lambda. That's going to be really easy. So I actually have a S3 object, which I'm just copying from one bucket to another. I didn't want to copy it from a local laptop up to S3 because conference Wi-Fi is always going to be awesome and mess it up for you. And so what's actually happened over here is currently I have no tasks running. So this ECS service is costing me absolutely 0 because ECS doesn't cost me when I'm not doing anything. But now what I've done is I'm going to be able to kick off a task. So if I literally refresh this, and the demo gods are not behaving, that should have copied. Because I'm looking at services, not tasks. So promise you I wasn't lying. There wasn't any service over here that was running before that. It was entirely free. Nothing was happening. I've just set up this task to run. As soon as I've done that, what's happened is files landed up in S3. It's gone to Event Bridge. Event Bridge is told step functions. Step functions says, what's the size, what's the size? This is going to be bigger than I wanted to do to Lambda, and then has kicked off this task. And so this task has started 10 seconds ago. If I look at the task, I can see all the configuration. And this is 4 virtual CPUs and 30 gig of memory. So a Lambda function can only be 10 gig of memory. So I'm already using Fargate because I've got more computing power. And so off this is going. So this is going to run. It's going to do some image processing on this. This would be one of the world's boring demos if we waited for 20 minutes just watching an ECS task happen. But I thought I'd just switch over to step functions. So we looked actually in the code that this was the step function state machine. And the cool thing about step functions is the step functions has actually got an invocation that is running. If I select on that, I've got this awesome picture which shows me exactly what's currently happening. So on my image size, I can look at the input, and you can see really simply this came from S3, and it will have a S3 bucket name, and it has got a video file, and there is the size. So that is the size that step functions was doing that choice state on, and that's the output of the state. So the output of the state, the choice state was go to ECS run task, and that is basically going to give that ECS task the S3 details. And so also it is sending on, there's the bucket name, and it's got the key file. And so within my ECS task, I'm just downloading that file from S3, doing whatever processing I need to do it. And then I've got a sort of another step which hasn't run here, which is going to run. But how cool is this, that I can have a workflow that I can see visually, and I can see exactly what is happening. And that's obviously all on the happy path. I'm not going to wait, but if I show a successful one, you can see that, that did the image size, ECS task ran. I can look at, don't want to select on that. I looked at the inputs, I looked at the outputs, and the output over here will give I think I've populated a time that was going to happen, and that then sends it over to another thing in the workflow. I can do anything, and then ultimately, whichever step it's going to do, this process is going to do an event bridge put events. Now, this cool thing is on the event bridge put events, I will show you over here if I actually look at the state machine, is we've obviously got custom code that is running here in ECS and Lambda, but this event bridge put events is once this is finished, I'm just going to say, send something to event bridge. I don't have to write any code for this. This is what Step Functions has as a direct SDK integration. And all it's saying is, here it is. Tell me this video details. We've got sending some information. I've got a source, and it's telling me put it on the event bus. I've got a source of serverless video, and it's just going to say that this recording is ready. So I could have a downstream service that is then going to take this information and is going to be able to react in an event-driven architecture way. But I'm not writing any code from the ECS task to put something on event bridge. I'm just allowing Step Functions to do that. The advantage is, first of all, I've got a visual workflow. I can see exactly what's happening. I have no code to maintain. I mean, all the configuration that is in here is to make that work is literally over here, and I've probably even got more information in here than I actually need. So a really easy way in a sort of low-code approach. This configuration is never going to go out of date. There's no patching. There's no optimization. There's no Node or Python or Java code that I'm running to do that. So super helpful. Step Functions has these native SDK integrations. Anything, or most anything you can do in the SDK, you can do directly in Step Functions, and I think that's over 11 or 12,000 SDK things. So if you think of reading from DynamoDB, writing to DynamoDB, starting an insert of data into Aurora, a batch, glue, Lambda, literally anything you can use the SDK calls. So yeah, super powerful, really nice way you can build event-driven architectures. You can see here, in a way, this is a mini microservice. So when I was talking about the difference between Step Functions and event bridge, we are showing here an example of that. That start thing is actually something that's happening in Event Bridge. Think of it as another microservice. Comes in here, does my choice state, does my video processing, puts an event back on the event bus. I've then got another microservice that kicks off and handles that, and then carries that on. And I can have multiple microservices handling this video. So for example, the video has now been processed. It's been analyzed. I could use machine learning. I could use Gen AI to create some subtitles, or some other machine learning thing to do a transcript. I could do anything, build these impressive event-driven architectures, combining the two together. So the question you're thinking of, hopefully, is, well, which compute option should I actually use? Which is right for my application? So let's go through some of the considerations. So there's some architectural considerations which I think hopefully you've picked up here today. And some of them on the Lambda side is, well, those triggers are managed. The runtimes are managed. We're going to patch Node for you. We're going to patch Python for you. We're going to manage the triggers. So when something from API Gateway or something from Event Bridge comes in, you don't have to manage all of that. Lambda's going to do that for you. And of course, any of the security and the scaling is managed by AWS. It's not all of the security. So for instance, in your Lambda function code, we may look after the node as the runtime, but if you've got dependencies or you've got modules or things that you're importing into your code, you still need to look after that. And the scaling is managed by AWS. We saw the demo earlier. That sharp scaling, you didn't need to configure anything and do that. On the container side, well, it's your custom code, your services. It gives you a lot more flexibility that you can use a lot of different services. Any code you can run in a container, you're going to be able to just run that, respond to things via an API. You're going to be run these services or running these tasks. But the caveat with that is, well, there's a bit more management and orchestration that you need to do for yourself. Then in terms of resource considerations, we touched on this a little bit earlier. A Lambda function can run from 128 meg RAM all the way up to 10 gig, and basically you only configure the memory. And then that's proportional CPU, and then proportional network, which is going to be configured, and you've got one performance lever, which is really easy, just to configure the memory. It can run for a maximum of 15 minutes. That's just one of the ways that Lambda works. As I said before, you need to do something longer, you use another service, or you break down your job into things that can run under 15 minutes. And I spoke about that sort of single concurrency. So one event comes at a time to run that Lambda function, and that means that, that scaling, that concurrency happens as part of a single concurrency model. And the cool thing about that is that's sort of really easy to reason about. Once you sort of wrap your head around it, you know that you upload one S3 object or one HTTP hit on your website, invoke a single Lambda function, and you just sort of understand how that works, and it's actually quite hopefully conceptually easy. On the container side, well, you've got way more variety, which is super useful. So, a quarter of a CPU all the way up to 16 virtual CPUs and up to 120 gig of RAM. I think that that may even be a little bit higher now. But yeah, lots more gigabytes of memory that you can add to your task. Loads of different networking modes. Anybody using the container world, when it's more a port and socket model rather than just the event-based mode, means there's lots of different networking constructs that you can use to connect all things together. And no 15 minutes, unlimited running time. This can go as for long as you like. And then also there's multi-concurrency. So if you have a Flask app, or you've got something like that that's going to be running a website, you can obviously take multiple requests. It's going to then come in via a load balancer. And this is a way that you can really get a huge amount of compute power and use the sort of power of containers with a multi-concurrency to process the same thing at the same time. If anybody's using Node.js, for example, you think of the event loop. This is the kind of efficiency that Node allows, that the event loop can just keep processing multiple things at the same time, which it doesn't do with Lambda. So in terms of the pricing, well, sort of the headline thing to think about is Fargate is you pay for what you provision, and Lambda you pay for what you use. So Fargate, a task spins up, you pay until it shuts down. Whatever happens in that time, you're going to pay for it, but you can do as much as you can in that time. So, for example, here we've got multiple tasks running, multiple requests are coming in, we've got high throughput, we've got high concurrency, and this is just an awesome way to have a whole bunch of compute power. And so in terms of pricing, you're going to pay per container instance per second, and that's based on the CPU and the memory that you're going to configure for it. And there is a minimum of a one-minute charge. That's just how it works. And it's a constant price, regardless of what's going on inside that container. Obviously, if nothing's going on inside your container, you're either wasting money or you're scaling up for a bit of headroom. So this is certainly going to be the lowest per request cost when the concurrent traffic is high and your code is also efficient. On the Lambda side, remember we've got one request at a time, so you pay for what you use, not pay for what you provision. So when a Lambda function doesn't invoke and it finishes, Lambda's just going to say, oh, hang on, I'm going to pause, and there's going to be no charge, and that's directly going to scale to 0. Then as soon as another request comes in, your Lambda function is just going to spin up, run its work, and then go back down. So you're going to pay per millisecond. There's no minimum billing, nothing like that. This is a really efficient, granular way that you can do your costing, where you're able to charge per invoke. And the pricing model is on the duration per invoke and on the memory size of the function. So obviously, this is going to be really cost-effective when there are gaps in the work to do. You haven't got multi-concurrency. You've got single concurrency. Obviously, they can scale up individually to super high scale. But yeah, if you have a whole bunch of work that's going to happen within one single container, that's going to be more cost efficient, but this is going to be certainly easier to manage and a different way of thinking about it. So some ideas on selecting between the two. You can use serverless containers. It's going to have a lower startup latency than EC2 autoscaling, for example. There's not a whole VM that needs to come up and take a whole bunch of time. Anything that you need a long-running compute job, longer than 15 minutes, obviously you're not prevented from running Lambda. If you've got predictable high-traffic usage, maybe you've also got some data persistence. That's another thing. So if you've got EBS volumes can be attached to ECS tasks. So if you do have some data in an EBS volume, you're not able to leverage that within Lambda. It's another consideration. And of course, when you do want some more control of your compute environment, you want to choose some different instances. Even if you are going EC2, you've got a lot more choice over there. That's why you would pick. That's not the serverless containers. That's sort of server-full containers. But that's another consideration point you may have. And also with the tooling consistency. Huge amounts of container tooling out there. This is just a container. It's going to run on your laptop. It's going to run in the cloud. You've got maybe CI/CD pipelines. You've got observability tools. All those kind of things are just really easily going to nicely wrap in with containers. There was another slide which said serverless functions, so I will just, must have hidden that slide. Anyway, what I'll say is, you'll pick serverless functions if you do want to sort of outsource any of that management and maintenance to AWS. You want us to handle the scaling for you. You want us to handle the patching for you, most of the patching of the runtime. You just want to be multi-AZ by default. You don't want to worry about things, spinning across AZs, all that kind of thing. That's where you're going to use. That's where you're going to use Lambda, and that's when you actually deliberately want less control. You want to focus on your business value. You don't want to be, messing around with compute instances and doing all that kind of thing. Lambda's a great choice going to be doing that. And so there's sort of this sweet spot you can think about it. AWS Fargate is going to be really good if you've got thousands of concurrent requests, a lot of requests, and it's stable and predictable on the different access. And you can think of this as the sort of intensity scale, how much concurrency do you want, and the stability scale, how predictable is it. Then Lambda is going to be really good if you've only, you've got a few requests at a time. As we saw with the 10,000 request scaling, that is still pretty high. So don't think that Lambda is sort of only for sort of really small applications. That's the way it's going to work. And of course, if it's got spiky workloads, off hours, off in the evening, off during the day, weekends, this kind of thing, again, you don't have to think about it. Lambda's just going to scale up and down as needed. Simpler please, you give me too much information already. So ECS Fargate is great. You've got long running, these are stable tasks, high volume, and high resource event sources. Then that's a really great way to use ECS Fargate. And then for the rest, you want the simplicity option, you want the event-driven option, you want the managed runtimes, all that kind of thing. Lambda's going to be the happy one for you. And of course, nothing changes. Everything moves all the time. So we're going to be building more well-architected fundamentals. These serverless services means best practices are built into the cloud. We will do that for you. Good developer experience. We're going to improve the controls, and we're going to, more and more integrations are going to happen over the time. So if you bet on serverless, things are just going to improve all the time. As you saw with some of the scaling improvements before, serverless has got your back. It's going to improve whatever you're going to do. Thank you. Hopefully you've got some information today about choosing some serverless compute for your event-driven architectures. I'll be around for questions as well. So thanks so much for joining.